Thanks for joining today. Our speaker today is Aaron Alexander, who is a postdoctoral researcher at the University of Wisconsin-Madison in the Water Resources Engineering Department. He obtained his PhD in 2025 from UW-Madison in the same department, where his research focused on urban resilience and land-atmosphere interactions of widespread greening in the Milwaukee area. Though his master's and PhD are in water resources engineering, his background is in atmospheric science and applied physics, so we've nerded out together quite a few times. And he uses hydrometeorology to examine societally relevant questions at local scales. When not working with WARF and NOMP, he volunteers on the Precipitation Technical Committee at AGU and helps build community for queer, BIPOC, and first-generation students and academics at UW-Madison. So with that, Aaron, take it away.
Awesome. Hi, everyone. My name is Aaron. Thank you so much for coming to this seminar. And I did cosplay as an assistant football coach, but I promise today we're going to be talking about urban hydrometeorology and greening. So let's start off. We live in urban areas. I know that's shocking to everyone. If we walk outside, we're like, oh my gosh, we live in a city? Who knew? That's important because both we are in an urban population and having a lot more urbanization occurring over time, as well as it's kind of becoming a rapid changing and evolving system where we have a lot of consequences that can occur. So 81% of the US currently lives in a urban space, with around 90% proposed to be living in an urban space by the year of 2070. So that ends up causing a lot of issues. And some of those issues are flooding. So if we look in at my study area that I like to look at a lot, which is Milwaukee, Wisconsin, we can see that there are places that have a large amount of flooding and places that have a small amount of flooding. This was done using satellite remote sensing from Tang et al. In 2022. And one thing that we can note from this is that locations that have a large amount of pavement are going to have inherently a larger flood depth on average, given the same amount of rainfall, which is what this plot is showing. At the same time, we have this other co-occurring consequence that happens, which is heat. So in places that have large amounts of pavements, we have a large amount of heat usually occurring. And those two things are going to be interrelated with one another. When we have locations that have a large amount of pavement or a large amount of sidewalks, a large amount of buildings, those are usually the locations that have the largest amount of heat. So if we look at this downtown region in Milwaukee, Wisconsin, we can see that we both have a double whammy of large flooding risk, as well as more than likely than not higher heat impacts. But interestingly and importantly, the reverse is true in urban spaces. If we look at this park in the northern part of Milwaukee, Wisconsin, we can see that a highly vegetated location is going to have less of a flood risk, as well as a less impact on heating. So we're going to have a better experiential temperature for those who live there. So that is great. Those are two hazards that we should be thinking about when we think in urban spaces, but there's also kind of unexpected consequences that happen in urban spaces from an atmospheric sciences perspective. So one of those is that when we have urbanization, we have an increase in flooding, as we just discussed, as well as an increase in heat. But we also have this heat and flooding mechanisms kind of working together to create a rainfall enhancement where we can have urban rainfall intensification. And then that becomes a sort of double whammy again, where we have a large increase in the amount of flooding that's occurring. So we have more intense rainfall, we have more intense heat, and that more intense heat becomes more intense rainfall, and therefore we have more intense flooding. And then we have an increase in urbanization. This is also likely going to get worse when we start to think about anthropogenic climate change. So as we discussed at the top, we're going to have more people living in urban spaces as time goes on. We're going to then have more heat, we're going to have more flooding, and then we're going to have likely more rainfall enhancement. I want to spend a little bit more time talking about this rainfall enhancement because it's pretty important for parts of my research. So when we think about urban rainfall enhancement or intensification, there are different mechanisms that can occur, and I've tried to simplify this down to the most bite-sized way that we can. Say that we have an air mass that's coming from the west that's preferential for rainfall already occurring. So it should be moist, it should have some convection occurring. As it interacts with the city, it's going to reach heat and also increase the amount of friction. This together is likely going to cause the air to slow down and want to rise. As air is rising, we do end up having moist rainfall, or we end up having moist air cooling, and then we have this rainfall. Now, if we were in a city that wasn't Milwaukee, Wisconsin, this would be where we would end this discussion, because we would have an intense amount of rainfall that happened over the city center and downwind. We don't have that problem in Milwaukee because we have Lake Michigan. Lake Michigan actually causes a re-intensification or a stalling of many convective storms that occur over Milwaukee itself. So what actually happens is, instead of having just a urban rainfall intensification downwind, most intense rainfall totals occur in and around the downtown area. So it's very important from a management perspective, to try to fix that. So I've talked a lot about problems. One of the ways that we can kind of fix this is we can use nature-based solutions, green infrastructure, low-impact developments, pick your name. You could just say green things in a space and someone would be like, ah, yes, I know what you're talking about. Qualitatively, that means that we're going to move from a city that looks like this to a city that looks like this, where we've added in tree canopy, we've added in downspout disconnection, we've added in things like green roofs, and we've added in things like permeable pavements. Now, when we start to look at these in individual locations, we have a really good idea of what's going on, but we don't really have a good idea of what occurs when we work at an entire scale, or the scale of a city. So when we try to test the importance of these processes at city scale, not just in neighborhoods or at street level, we need to turn to sort of city scale models, and in my case, I look at coupled atmospheric models. And so to kind of give a state of the science of what is in these models, if we go back to these nature-based solutions, there's no trees or no tree overhanging canopy that occur in most urban models. You can have trees sometimes, but that is going to be in very highly specific, doing a lot of work to use them. There's almost no way for water to move in between land covers in most urban models, so we do not have fundamental hydrology being represented. And there is some green roofs that are like urban canyon model that we have within WRF right now, but that is only going to be usable inside of the urban canyon model, and you may not want to be using that. So it becomes kind of a tricky situation of lots of more parameters are introduced and not something that you may want to be using. So as I've kind of already hit, the problem is for my work, if say the city of Milwaukee comes to us and says, we want to know what is going to happen when we add in our $100 million green infrastructure plan across all of Milwaukee to try to add in green infrastructure everywhere, we don't know what's going to happen because we have site-specific studies on heat and hydrology and extreme heat, but we don't know how that's going to feed back at city scale. So throughout most of my PhD work, I ended up creating a new land surface model that's called NOAA-MP for heterogeneous urban environments, or NOAA-MP-HUE, and that's sort of the center of what I've been doing in the Milwaukee area. NOAA-MP-HUE allows us to represent urban trees, so we have different land covers for an urban tree and an urban tree that overhangs pavement, and we allow for soil water to be fluxed through the urban tree that overhangs pavement and is accounted for correctly. We also have the ability to transfer water between impervious surfaces, so bioswales, turf grasses. We have also added an in-house version within NOAA-MP itself instead of in an urban module, bioswales and green roofs. So that way we can be taking account of the updated physics that is within NOAA-MP and not relying on physics that was already occurring in the urban canyon model, which is mostly based on the NOAA land surface model. So if you want, I'm not going to be going into a lot of what NOAA-MP does. You can go to Alexander et al. 2024. I'm actually going to be talking a lot about what NOAA-MP-HUE gives us in terms of accuracy for the first part of this talk. So what we're going to be talking about at the beginning is what happens when we use NOAA-MP-HUE in a current climate under current management scenarios, which means what is the current land cover looking like? So to be able to do this, as part of my PhD work, I used the weather research and forecasting model using two domains, domain 1 at 9 kilometers, domain 2 at 3 kilometers, and I ran this for 12 different summertime events. There are both rainfall and heat waves events within these, and we are going to be showing 2 different simulations per event. We actually ran 3 per event, but for sake of time, I'm only going to be showing off 2. And that means we're going to have one that is of the typical model. I'll explain what that means at the next slide, as well as one using the NOAA-MP model. So for the typical model, I'm using the out-of-the-box WRF urban model. This is what is widely used in many applications, including CONUS 404. I want to make sure that we understand that at the beginning, because I'm going to show some slides where everyone's going to be like, oh my God, and I'm going to be like, yes, that's in CONUS 404. So what CONUS 404 does, or what the typical model does, it says we have a single land cover type in our grid cell, and if it is suburban or heavily urbanized, it's going to treat it as a flat piece of pavement, and it's going to have a differing albedo, emissivity, and surface roughness, and that's it. The other model that we're going to use is the NOAA-MP simulations, where we have multiple land cover types in our grid cells that are being spatially averaged together to create a more representative flux. And in this case, we're going to just be looking at the effects of adding in tree overhanging pavement, as well as adding in downspout disconnection. So adding in water that's going to go from a homeowner's house into a surrounding turf grass. And you can see already that we have a very much different looking spatial pattern of something that is more representative of an urban space itself, instead of just a square wave almost. So I mentioned that I've done 12 different events, and I'm only going to really be focusing on 11 of those events, because one of these events, event A, which is the heat wave of record within the Milwaukee area, behaves super differently. We're going to return to it later, but we're actually going to be looking at aggregates of 11 events. So there's 1 heat wave in there, as well as 10 different convective rainstorms. I just don't have a billion years to talk up here, or I could. So let's get into some results. We're first going to be looking at 2-meter air temperatures and sensible heat fluxes. I have gone through and I've worked this in terms of peri-urban, suburban, and heavily urbanized. So peri-urban, what I mean is locations that are within the Milwaukee area, but are actually not going to be an urban tile. So in the northern part of Milwaukee, we have a large amount of agriculture, and in the southern part of Milwaukee, there's a forest. So both of those are going to be within like the management area, but they're not going to be well represented, or they're not going to actually be an urban tile. Then in our suburban area, these are going to be locations where we have some changes to more like single-family households or duplexes, something like a Longmont, so to speak. Then we're going to have our downtown city center area, which is going to be like downtown Denver, lots of skyscrapers. It's actually quite densely urbanized. If we look at both the average air temperature map that occurs during the daytime, as well as our diurnal patterns of our sensible heat fluxes, we can note 2 very important things. The first thing is that the heavily urbanized and the suburban heat fluxes are almost the exact same. That is because there's almost no difference between how they are being treated. And this is causing a big jump in terms of what the air temperature is actually averaging between peri-urban and our more urbanized land covers. Likely not physical. If we look at hue, and then we also look at the difference that we get when we do hue minus typical, we can see that we get a much more realistic representation of what an urban space likely should be. In the peri-urban space, we see almost no difference. We actually get an enhancement of sensible heat flux because we're representing smaller tiles of urban locations. And then within our suburban location, we actually get a major reduction in sensible heat flux, as well as in our heavily urbanized spaces. And corresponding to that, we get a decrease in air temperature on average within the suburban and heavily urbanized spaces of around 2 degrees Celsius. We can do the same sort of analysis for the surface humidity and latent heat fluxes. So within the peri-urban space, we can see that we have an actual latent heat flux diurnal pattern. But in the suburban and heavily urbanized space, this is a flat piece of pavement. There is no vegetation. She can't evapotranspire. So she's not going to. So we get, again, this wave, this sine wave almost, or this square wave of no very low humidities. If we look at what no NP gives us, we get a higher amount of humidity throughout our entire urban area, and we get an enhancement of what suburban and heavily urbanized latent heat flux, just because, for in this case, the bar is on the ground. We are actually having latent heat fluxes, which is good. One thing that is also really nice about working with multiple events is that we can do an event error aggregation. So if we look at what 2-meter air temperature observations give us in terms of what the typical 2-meter air temperatures were from WRF, and then what was observed at multiple locations across all of Milwaukee, you can see the locations of where those are in the map. We can see that we have a pretty high root mean square error. We have a really good Pearson's correlation, but we are biased warm, which is not necessarily shocking given the fact that we don't have any vegetation. But when we look at hue, we get a general decrease in our root mean square error, so we are doing better. We get almost the exact same Pearson's correlation, so we are doing the same in terms of our diurnal patterns. And we are now doing a better job of, we are still biased high, but we are not biased as high. So while this is not necessarily a panacea of fixing every error that we have in urban spaces, this is doing a lot to get us to a better location for our analysis and forecasting. That's all I'm going to be really talking about for the surface energy fluxes. I do a lot more in this paper, which is Alexander et al. 2025. I even go into specific humidities and also show that this change that's occurring is not due to changes in available energy. It's actually due to changing evapotranspiration and the amount of water that is allowed to be used. So I spent a lot of time at the beginning of this talk talking about urban rainfall intensification. So now I actually want to show urban rainfall intensification in the Milwaukee area. So with NOAA MP, we can actually start to examine how urban hydrology may be influencing convective rainfall events. So that's what the next couple of slides are going to be focused on. This is a map of aggregation of 3 storms. We did an analysis of 10 storms, but I've picked out 3 that are very special because they do have this sort of Lake Michigan reintensification that occurs within the observations. And we can see that with AORC, which is just a gridded precipitation product that uses radar and some gauges to help bias correct at relatively high resolution, 3 kilometers at 1 hour. If we aggregate them over the entirety of our storm events, as well as overlay the Milwaukee Metropolitan Sewerage District's high-resolution rainfall rain gauges that measure at 5 minutes, we can see very clearly that there is an urban rainfall intensification pattern, this little thumbprint, where the downtown area has the highest amount of rainfall, which is sort of antithetical to what urban rainfall intensification occurs in cities that don't have Lake Michigan. Now, if we look at what the typical model gives us over the same rainfall events over the same time period and look at their differences, we can see that we get an underprediction of rainfall in this very critical area of urban rainfall intensification. But if we look at the hue model, we actually get something that's very close to what is being observed, both spatially from AORC as well as at our point locations. We get a nice reduction in error. Again, I'm not saying that this is perfect because if we look at the very north and very south of Milwaukee, we are getting an overestimation. So we are still going to be suffering from issues with the influence of sea surface temperatures in Lake Michigan, changes in the boundary layer properties and how those are represented in WRF, as well as microphysical parameterization issues. But we are doing better, and I think that's a win. We can do one step further to look at the mechanisms of why are we doing better. And so if we look at the integrated water vapor transport at the low level, so between the surface and the top of the boundary layer, which we set to be about 1,200 meters for this analysis, we can see that during these specific rainfall events, we have an enhancement of IVT coming out of the Milwaukee area compared to what is occurring in our typical model. That means that we have more water vapor available and is being swept away towards a center of convergence in this case. We have low-level convergence that's occurring, so we're going to be moving our air upward. And that is not necessarily the case for the typical model, which causes this sort of underestimation. And then if we look at the resulting rainfall that occurs after the most intense period, we end up getting something where we have a better rainfall map, so to speak, of during these events. So that is what we can get from a current climate and a current management scenario. I'm now going to be talking about ongoing work that I have going on, where instead of looking at current climate and current management scenarios, we're looking at future management scenarios. So we're going to be actually integrating and adding in green infrastructure. So if we're thinking about trying to add in green infrastructure into a city, we have one thing that we should be thinking about. Where do we place it? Well, we're very lucky to be working with the Milwaukee Metropolitan Sewerage District because they have an in-house metric that ranges from 1 to 5 of where they are planning on putting green infrastructure that is at the sewer shed scale. So these are the sewer sheds that are within the Milwaukee area. And for those who don't know, a sewer shed is just a watershed in an urban space. They're effectively the same thing, they just ignore topography, and we've just engineered them. So this in-house greening metric allows us to add in information about hydraulic and hydrologic possibilities of adding in green infrastructure. Ecosystem services, so is adding trees going to actually help our ecosystem? And socioeconomic constraints and concerns, so is this a particularly BIPOC location, and would this actually be beneficial to the society if it was added in? From this, we can upscale our greening metric to something that is actually being able to be used at our wharf grid, which is shown here. So we have now a metric that gives us less greening potential to more greening potential. And we're going to be using this to be able to decide where we're going to be putting greening infrastructure in this case. So now we have this. We have sort of a way of being able to say, we are going to put green infrastructure, a lot of more green infrastructure in the center than at the periphery. How are we going to know what to put? Well, we have to go and do image classification, which made me lose the rest of my hair, so we're not going to go into that a lot. But what we're going to do is say we have a tile, and we are able to go in and say there are different land cover types within that. And the land cover types that we are going to be looking at are urban trees with canopy that overhangs pavements, which is the very lightest green and the light green, and then pavements that drain to those trees to add for self-watering that can occur. We can add impervious surfaces, which are buildings, roadways, and sidewalks. Turf grass, which ends up being a residual because we believe we've accounted for everything except for turf grass. Non-urban trees, we decide that there are trees and non-urban trees based on if it's in a park or in a forest comparatively to like a city street or in a yard. And then we also add in water and other NLCD land categories such as agriculture and whatnot. So once we have that, we can go in and say this is what our baseline is at each pixel, and now we need to create something that looks like a full policy or what is planned on being added. To give you some numbers on what Milwaukee is trying to do, when I say we're adding trees, we're adding 1.5 million trees across all of Milwaukee. So that requires us to go in and say, we gotta make some rules, and so some of the rules that we've added are we're going to be adding in trees, that some of it is going to be adding into trees that overhang pavement, and then we have to add in extra tree canopy or add in extra pavement that runs on to these trees, as well as extra trees that are non-urban, as shown sort of in this pictograph that I've created. We also have to add in things like green roofs. They're planning on adding 1,180 acres of green roofs across the entire city. So if there is a building that is not a single-family home-owned building, so something like NCAR, we say it's eligible to put a green roof on, and then we add a green roof if that pixel needs it. We also are going to have to add permeable pavements, so only roadways are going to be eligible for permeable pavements. We need to add in downspout disconnection. So downspout disconnection in this case is going to use tax parcel data to try to find single and dual single family and duplex family homes in all of the Milwaukee area and say, oh, you're fully disconnected if you can. Very hard, very crazy. And then we also are going to have to add bioswales. And so bioswales in this case are going to likely be on the edges of parks, and they're going to have large amounts of pavement that are going to run on to them to help them drain. So we did this for a full policy. So each pixel goes from something that looks like the baseline circle to this interlaid pie chart with our full policy with all of these conserved. And then we have an extreme case where we've taken everything that we've added and we multiply that by 1.5 to try to see what could possibly happen. As you can see, things look very different, and we're expecting to see large differences. So because we are currently running these simulations, we're planning on running 15 years. I'm going to just be showing 1 year. I'm going to be showing the greening or the growing season of 2022. So when we add in green infrastructure, we actually end up getting a change in runoff, and that leads to increases in deep drainage and evapotranspiration. So if we take our full policy and our extreme policy and look at how much runoff occurred at each pixel, and we subtract what the baseline simulation occurred or was doing, we can get maps that look like this over our entire growing season. So this means that we have a general decrease in runoff, and that decrease in runoff is going to be mostly focused on our highly urbanized spaces in the center of the Milwaukee area. To make this a little bit more number-centric, I've added in a bar plots that we're going to be able to see and follow as we go down. So if we look at just the runoff flux, we see that we have about a 1 part change from baseline to full policy, and then that baseline to full, or full policy to extreme policy is about, again, another 1 part of that 1 part being around 75 millimeters of runoff reduction. Deep drainage, which is the amount of water flux that could be going to groundwater recharge, increases, and we see that we have a large increase, again, sort of co-located with this highly urbanized space. Then finally, we can look at the evapotranspiration changes. While there is an increase in evapotranspiration that occurs across most of the Milwaukee area, there's not as large of a change that we would expect, but this is likely because 2022 was a really wet year. There was a lot of rain that fell in these simulations, so we're likely energy limited, we're not water limited. So we're not going to be expecting to see a large increase in evapotranspiration. So this is sort of the high level changes that we get for our hydrology. We can also look at heat. One of the things that we track in the Milwaukee area is the number of 90-degree Fahrenheit days. That's important for our state climatologists and helps our decision makers on the ground in MMSD say if they need to be releasing a warning or not. So that gives us a natural thing to be able to categorize. If we look at the number of 90-degree Fahrenheit days that occurred in our 2022 simulations, we get a baseline that looks like this, with most of them occurring in the downtown area, especially that pixel that's right on the lakefront where we have our most heavily urbanized spaces. If we look at what the full policy change gives us to the number of 90-degree Fahrenheit days, we get a decrease, and we get a very similar decrease that occurs with this extreme policy. Again, I want to bring up the idea that we do not have a very big change in evapotranspiration that's occurring, and that evaporative cooling would be the thing that would be causing a reduction in our heat in this case. So we can then look a little bit more at these days we had 90-degree Fahrenheit or had a change in 90-degree Fahrenheit and look at what the sensible and latent heat fluxes are doing. There's not that big of a difference that occurs in the sensible heat flux during the middle of the day. There is a slight reduction, but most of our change is occurring within the latent heat flux itself, so we do have a slight increase in latent heat. Now, just because our dry bulb temperature is changing doesn't mean that we're actually changing our experiential heat. We need to look at things like heat index or the wet globe bulb temperature. I chose heat index for this, but we are calculating the wet globe bulb temperature in our current simulations. And one thing I want to point out is while we do have a general decrease in our heat index that occurs during the middle of the day from our full policy, we get this rebound effect that occurs where when we've added in too much greening, we actually re-increase that heat index. So there could be a point from a management perspective that we've gone too far, and cuidado, we should go back. We've greened too much. Now, to add in a further complication and excitement to this work, I want to think about some of the bigger atmospheric changes that could be happening. Remember, we're using WRF, which means that we have changes in rainfall that are occurring. So this now becomes, instead of a static problem, something that every year and every simulation has its own rainfall in every pixel. So figuring out how to be able to communicate that and understand what these changes are is quite tricky. So the way that we've started to run is if we look at this full policy change and this extreme policy change, we could be seeing that by adding in extra greening, we're actually causing a reduction in rainfall in and around the downtown region. So to be able to verify this, that's why we have to run a bagrillion more simulations, which are currently going on derecho. We love her. So stay tuned for that one. Now, that's sort of the end of my talk about current climate and future management scenarios. I now want to turn to future climate and current management scenarios, where we can start talking about extremes that we could be seeing in a future climate. So do we recall this plot where I kind of like kicked the can down and was like, oh, we'll return to it? Well, we're returning to it. We're returning to this heat wave specifically. This is a really good heat wave to be able to look at potential changes in extreme heat within the Milwaukee area. So the 2012, oh my gosh, 2012 July upper Midwest heat wave was the most extreme heat wave that Milwaukee has experienced. It was over 100 degrees for like 7 days, even more so in some locations, and it did end up unfortunately killing 4 people. This is potentially indicative of future heat waves. This heat wave was very slow moving due to a high pressure system moving in, and it had low soil moisture, so this was sort of a compounding issue. We had a high pressure that just sat over Milwaukee. We didn't have a lot of soil moisture for evaporative cooling, and then Bob's your uncle, it's bad. The most intense heat wave, or most intense temperature in the Milwaukee area occurred on July 5th with a record high that's still to this day at 103 degrees Fahrenheit. And one of the things that the Milwaukee Metropolitan Sewerage District has asked us is they want to know how this event could potentially change in the future, because they want to know if eventually this green infrastructure that they're trying to put in is actually going to help them to be able to be resilient to these sorts of things. Well, we know as a scientific community, when we're thinking about models and we're thinking about WRF, one of the things that we can use is pseudo-global warming methods. So let's talk a little bit about that. If you've never heard of pseudo-global warming methods, that's fine. I have a pictograph to walk us through. So the current methodology for changing, looking at events and changing extremes is to use a pseudo-global warming method. So let's say that we have our current climate and we want to gather all of the times that occurred within a climactic period for that event. So in our case, we have a July event. So we want to collect all of the Julys from 1990 to 2020. And so we get July 1990 through July 2020. Then we want to do the same thing for a potential future climate. So we want to know at the end of century here, so we're doing 2070 in July to 2100 in July. Then, very simply, we take an average of everything that happened in the future, we take an average of everything that happened in the past, we subtract them, and then we have a delta. This delta allows us to now superimpose what occurred in the potential future onto this event, and we can now run it multiple times. If we use a data set like CESM Lens 2, for example, we get 100 different perturbations that we can superimpose on this event. This is what we did. I ran all 100 events over the Christmas break. It was so fun. I had a sinus infection. It's fine. So we ended up getting a sort of delta that can look like this, where we have a temperature change or a temperature distribution change of each gray line is a single CESM lens member. And then we have the same change that occurred for humidity, There are different ways of doing PGW. We have changed everything that we could. So the U, the V winds were changed, the temperature was changed, the humidities were changed. We did not change Q directly. We changed the relative humidity to make sure that we didn't have supersaturation occurring. We also changed the land surface at all points that we could, except for soil moisture, because soil moisture is tricky. We'll get into that a little bit later. One thing I want to note when we start looking at these delta patterns, that we have a really relatively narrow band of uncertainty. So while we may be becoming overconfident and saying that every potential future that we see is potentially around 5 degrees Kelvin warmer, or potentially 2 grams per kilogram more moist. So this is likely not going to be representative of what we expect to see a widely changing representation of future extremes. So that's why myself and colleagues, Aaron, shout out, have come up with a different idea that we've taken to create a pseudo-global warming extreme preserving methodology. So now, let's say, and simplify this even more, July 1990. If we go into a historical record, let's say we are using ERA 5, we can look over Milwaukee and we can pull out important covariates. In this case, we're going to be trying to find things like 2-meter air temperature, 2-meter wet bulb temperature, which gives us information on the evaporative cooling that could potentially be happening, and then the 500 hectopascal geopotential height, which is the important thumbprint of what this specific heat wave occurred. Now, one thing that we can leverage when we're thinking about heat waves is that they persist, right? They should happen over a long amount of time. So we can take a rolling average and then have this sort of smoothed out temporal pattern. If we then renormalize this so that everything has the same units by creating a z-index, we can create things that should be able to be added together without having to worry about any potential changes or unphysical things occurring. So that's simply what we did. We add all these together and we create what we call a multivariate z-index, and then we find what the maximum value was for that multivariate z-index and save the block maxima. We can now do this for all Julys that happened between 1990 and 2020, which is our period of record, and we have a distribution of what these heat wave-like z-indices should give. Seems like a lot of work. You're probably at this point being like, why are we here? Why did we do this? Well, if you remember, I said block maxima, which means we can use the generalized extreme value distribution, which is well used in PMP work and extreme rainfall, and fit a distribution and assign what the 2012 event was likely to a quantile. Now that we have a quantile, we can just do the same thing with our CESM lens ensembles, but in reverse, and create different distributions. Say this is the distribution using the same methodology from ensemble member 50 in the future. This is the same for, or that's the past, this is the future. We can then subtract them and get multiple changes to a delta, or we can get a new delta that is extreme preserving, that matches to each ensemble member's individual quantiles. So said in a different way that's probably less confusing, if I know what the 0.952 quantile is in each CSM lens ensemble member, I can just subtract those two and create something that should be more aligned with what the extreme delta is. If we look at the same profiles that we saw before, where this is the standard PGW method, and this is the quantile PGW method, we can see that we get much more scatter, which is good, because we should be able to start sampling more extreme tails of our distributions. And we also are keeping our average signal. If this line here is the average of both of these distributions themselves, they're almost identical. So we are still able to get both the average signal as well as the extreme signal. So now we can start to ask questions of does this potentially translate to differences in the 2012 heat wave? So we were crazy and we ran CSM lens perturbations 200 times, one for the traditional method, one for this quantile method. And now we're going to look at some of the results. Yay. So how intense could the 2012 heat wave be? When we start talking about ensembles, you have to be really specific about what you're showing. So I've created more pictographs because that's the best way I know how to communicate this. So if I take the maximum temperatures each day at each pixel and average them together, I get a map that looks like this. This is our historical reconstruction that we did, and we get an average heat wave intensity of 35 degrees Celsius. If we do the same thing for the standard PGW method, but instead of just averaging, we average in addition to maximums through time and space, maximums through time, space, and ensemble member, we get an average of this map, where we have an average across all of MMSD of about 39.6 degrees Celsius. And our quantile methodology comes in something with a little bit cooler of around 38 degrees Celsius. You'll note that most of the changes that are occurring are within the inland period or the inland part of this quantile versus the standard PGW. We can then sort of deconstruct what the standard PGW and the quantile PGW are doing if we look instead at the different distributions that we get. And we can see that the reason why we likely are getting a difference in the mean is because we have this tail that's occurring within our quantile approach that is dragging our mean down. But we do have a similar approach or a similar problem with our extreme tail, where we have a larger heat wave signal that goes up to almost 50 degrees Celsius at some points, which is quite scary and quite high. So what we can do to sort of see, is this a good gut check, is we can take, again, this maximum air temperatures from our baseline reconstruction, and we can subtract them for all days. So what I mean by that is if this is what the temperature looked like here at each of these 3 days, I can take each ensemble member and subtract those maps to create what I call delta distributions, and we can find what the hottest and coolest ensemble members are. When we look at that, we get a delta distribution that looks shockingly like the original distribution that we fed in to our WRF model, which gives us sort of confidence that things are happening physically. But we can now start to extract the warmest and coolest ensemble members. For our coolest ensemble member for our standard PGW approach, we get a change of around 4.1 degrees Celsius warmer. Our standard method, or our PGW method that is quantile based, gives us a decrease of 7.3. This could be because this is no longer a heat wave at all. So there could be extra thresholding that needs to happen. When we look at our warming signal, we get an average warming of 5.8 degrees Celsius, still a relatively narrow band, while we get a warming with our quantile approach of 8.5 degrees Celsius. So something that could be more representative of those extremes. So the question that we ask about why is this mattering is if this is the warmest standard PGW approach ensemble member that we can get, and this is the warmest quantile member that we can get, are we actually planning for the right extreme, or do we need to be thinking about things more aggressively at the management scale? So that's all of the overview I have of my work right now, but I'm going to give some inroads on what we're trying to do, where we're trying to use future management scenarios and future climates kind of together to be able to synthesize a lot of this work. Some of this is going to look like using extreme heat and nature-based solutions. So using this quantile approach and our full policy case to try to actually are we getting more sustainable futures with our greening that we have been adding in. We're also looking at trying to use this methodology for extreme rainfall. It's actually why I'm here. That's why Aaron invited me, to be able to try to get at an important flood event that happened in the Milwaukee area on the 9th of August in 2025, which is a state record holder now for the most rainfall that occurred in 24 hours, 14.55 inches. Crazy. That's a crazy amount of rainfall. Then we're also looking at trying to understand the role of underlying climates in our co-benefits of nature-based solutions. So we're branching out from Milwaukee in a NASA project that's where my postdoc is funded through, where we're now looking at Phoenix, Salt Lake City, St. Louis, Charlotte, and Chicago to be able to do this sort of nature-based solution work. I am now happy to take any questions, and I would like to thank my team for all of the work that they've done to support me. Thank you.
Questions for Aaron? I think I saw Chris's hand.
Great talk, and One question I had is if you had a chance to dig into the data for the first part of your talk where you were able to look at storms that formed locally versus those that were moving into the area.
Yes, so in a paper that is currently under review at GRL and will hopefully get published eventually, we were able to look at the different mechanisms between ones that are lake influenced and ones that are influenced from a large scale. And when we did that same breakdown, there were notable differences in the large scale that we still had more water vapor that was being ejected from Milwaukee that helped with this re-intensification. That was pretty interesting to see.
Thanks. Great talk and great visuals too. My question is so with the NOAA MP hue versus the standard or default approach, how much more computation or how much more computational expense is it to do that, where you're running all the tiles with apportioning different percentages to different land types? Because it would seem like that would be a no-brainer to just do, but I assume there's an expense and a cost to it.
There's an expense and a cost to it, but it's not as big as you would hope or think. Most of the computational expense that comes in WRF is actually from the microphysics scheme and the radiation scheme. So when we run for my second sort of topic area, when we're talking about those extreme greening options, I was running 15 different land cover types, and the change between baseline and the extreme greening type for one time step was 0.0002 seconds. So it is not that big of a difference. It will add up when you're doing 183 days of simulations like I was doing because, we're crazy, but yes.
Who next?
I think blue shirt and then, I'm not sure between these two.
And then there's also one online too.
Oh,
Yeah,
Andy.
yeah.
How do you go about parameterizing the turf grass lawns?
That's such a great question. So someone wrote a really good thesis in 1989 that I was in Phoenix that I was like, I love you. It had all of the parameters I needed -2. And then I was able to go and talk to the UW-Madison extension to be able to get a turf grass roughness and a roughness length from sort of ergoson measurements that they had been using in the field around the Milwaukee area.
Cool.
Yeah. The trickiest variable for that was LAI. The LAI of turf grass
That's the same thing in my simulations. The LA of turf grass
is crazy.
Excuse me. Hi, Aaron.
Hi.
Very great presentation. Yeah, I got to ask this quick question for the second part, the quantile PGW method. So it seems that the quantile PGW are sampling the variability from large CSM ensembles and then downscaling directly. So since it is a heat wave event and then imposing by ERA5 large scale, so the large scale circulation pattern is still like a blocking system, but in a cooler climate. So it does not necessarily quantify as a heat wave.
Yes, so that could be something that is happening. These were all analysis that occurred I was sick, December, we got here, the government did whatever it was doing. So I am looking into that once I get back to Madison and trying to figure out, is there a way that we can threshold things that are still heat waves versus not heat waves in our quantile approach? Because it's very likely that some of those are no longer heat waves.
And a follow-up question is, does WRF downscaling actually give you more variability compared to the original CSM ensemble?
Some of it,
something could look into.
yes, some of it, there is probably an enhanced variability that was occurring. We get the same idea of those delta distributions, but there is larger tails. So I think that is true.
Okay, thank you.
Thank you. Andy.
Yeah, thanks for your talk. So I have a more technical question about your hue in the NOAA MP.
Sure.
So as I know, the NOAA mosaic include a single layer canopy UCN.
Yes.
Did you use any urban canopy models?
I did not. No MP hue is able to be used with the urban canopy model or module. We ended up not using it because when you use the urban canyon model, you add in a ton more parameters that need to be precisely computationally tuned to be able to give us realistic values. And we didn't want to be dealing with that and dealing with this issue of, in our baseline simulation, is it being more controlled by, is it in the urban canyon model versus not in the urban canyon model? Our science question for that part was really looking at, are we having an enhanced representation of vegetation? Is that giving us a better result?
Yeah, because some of these urban canopy models already incorporate like urban tree, turf grass, green.
Some of them
roof,
do,
like
yes.
But you are doing at a land surface model, but not in the urban part.
Yes.
Urban canopy model. Okay. And the second question is about PGW.
Sure.
I always have the question about if this method violate the hydrostatic and geostrophical wind balance.
Mm-hmm.
Maybe questions to Connors for PGW group.
I do not, from what we looked at when we were starting to run both of the methods, that we are not actually violating any hydrostatic equilibrium or geostrophic wind balance. Everything is still in balance.
That's why we also vary all
Yes.
the different variables. So some PGW studies will vary just temperature, and then you are out of balance. But by varying temperature and winds and pressure, you maintain that balance.
Yes. You're welcome.
Can we do? Yeah. Okay. Cool. So Andy Newman has two questions. He says, "Hi, Aaron. Thanks for a nice talk describing your bulk urban tiling scheme. How does this compare to the explicit urban models within NOAA MP WRF in terms of surface, weather, and hydrology? Example, T2 fluxes, runoff, et cetera, computationally, and for the inclusion of nature-based modifications?"
That's a great question. So we were kind of getting at that with a previous question. The big changes that occur between NOAA MP-HUE and the canopy model is everything that is happening within NOAA MP-HUE is within the code base of NOAA MP, so we're not adding on any additional codes that need to be ran. The changes that occur are mostly that we get a warmer temperature that occurs with our urban canopy model when we run it with NOAA MP-HUE compared to our slab parameterization, which is maybe okay, but we were already so warm biased in the Milwaukee area that we ended up moving away from that and just using the slab model itself. There also is sort of like a secret like mosaicing scheme that already happens when you use the canopy model. But the big difference between the canopy model and NOAA MP-HUE is that the canopy model's vegetation is just a grassland, while our model allows you to have multiple different types of vegetation that should be representative of the actual what is happening as well as future conditions.
And then next question online.
Hey,
Okay.
Andy. Yeah.
Oh, and Andy's just listing these off.
Andy's like, I have to say something. Hear me.
Okay, well, yeah, he's following up with the balance in PGW. They're all out of balance because it's an average perturbation, but it's so small it doesn't matter.
That's probably fair.
Yeah. I need to think about that one more, but interesting point. He also had a question about the PGW, saying it's an interesting idea. Could you use the empirical CDF rather than a GEV? I also wonder about your spread, as you noted in your talk. Looking forward to discussing more.
Yes. So we had thought about using the empirical CFD instead of the GEV. The problem is with the methodology as how we've structured it, you're only going to have at most 30 values. So being able to assign a quantile accurately from 30 values from a C or a empirical distribution is not likely going to happen. That's why we went back and used the GEV model or the GEV statistical model.
Yeah,
Hi.
great. Thank you so much. And I swear I'll be quick, but
No,
it's really great contribution, I think, to the modeling and something that's well needed. So maybe first point is that do you know Sarah Mirau at Arizona State? Because we're working with her on some different green infrastructure design and looking at co-benefits of flooding and heat mitigation with Sinlin and some other folks here. So it'd be good to put you in touch because she's also working in Phoenix, but we're adding Detroit and Boulder to that. So maybe there's some overlap with the cities you're working on.
That'd be great.
Second question is, because we're struggling a little bit with this, so the green infrastructure design things, I speak from the hydrology side, but they're notoriously difficult to evaluate.
Yep.
Because you don't have observations often.
You're so right.
So how are you able to, have you come up with a creative way to evaluate these changes?
What we ended up doing and using is we said we can't get the hydrology because the values don't exist or would require its own field campaign. We ended up leveraging the observations from meteorology and said that those are likely going to be the things that are influenced by the local scale to then be able to say, oh, if we're getting the local scale right, we must be getting some aspect of the hydrology more correct.
Yeah, so kind of an indirect. Okay,
Yes,
got it.
there's no direct way that we were able to get.
Yeah.
You could try to do land surface temperature, which is something that we are exploring for this, for our multiple locations. But you have to be very careful that the land surface temperature that comes out of NOAA MP is a one-to-one apples comparison to land surface temperatures that we get from remotely sensed products, and a lot of times it's not.
Yep, right. Yep. Great, thank you.
Yes.
Oh, I can't throw that far. Come on, Nick.
You can kick it.
Hey, great talk. I had a question about the MMSD greening parameter or whatever it was.
Yeah, the greening infrastructure plan.
Yeah, how exactly was that determined? Because it seems like it greatly affects management plans that can be determined from that. Do you have any insight?
So, are we talking about the original plan?
Yeah.
Yeah. So that was in 2013 when they'd said that. I was in high school, so I wasn't able to help with that or know about what was going on. It seemed like what they were really looking for was trying to create a more sustainable area because they had just gone through what they thought was the worst flood that they've had, and then it got worse in 2025. So they were really just trying to get at trying to reduce the load that they have on their sewerage system. And so the cheapest way that they had to be able to do that within the main part of the Milwaukee area was to add in these nature-based solutions. So that was kind of their impetus. They have what is called a connected drainage system. So that means that when you flush your toilet, as well as if any rainfall happens, that all goes to the same sewage system, while there's a disconnected sewer system in the wider part of the Milwaukee area. So you have these like overflows that can occur in the connected portion that are really dangerous because they are public health concerns because there's literal poop water on the ground. And that's bad because cholera is a thing.
So does the metrics map that you showed that you translated into words?
Yes.
Like how? I guess I'm confused at how what determines those metrics? Like the places where is it where there's just like a lot of potential for greening?
It's the places that they could be potentially used or potentially for greening.
Okay.
So it's places that have a lot. From our perspective, it's locations that are going to have a lot of impervious surfaces, as well as locations that are going to be more socioeconomically disadvantaged. So the very northern or the north of the downtown area is a relatively poor location. And so that's someplace that they're really trying to target to try to help with some of the more extreme heat that they have in those locations. You can't, if you go too far north, you would note in the map, we can just flip back to it, not to put, I guess, MMS or the Milwaukee area on blast, you'll note that this area is not really a good priority for greening. This is where all the really rich people live. And there are like a billion different golf courses. So they're not going to be trying to green here because it's already very green. So that's sort of, they use a synthesis of swim modeling, remote sensing, as well as for the socioeconomic data, they use census data to be able to create this.
Cool, thanks.
Yeah, you're welcome.
I think we're out of time, so if you have additional questions for Aaron. Oh, Senlin had a question.
Hi, Senlin.
Yeah, so he said okay, thank you. When you compare NOAA MP typical and NOAA MPQ for LH humidity in the first part, did you keep the vegetation fraction for each grid the same in the two configurations?
No, we can't. Well, yes, we did, but that doesn't mean that anything could possibly happen with the vegetation fraction if there was no vegetation allowed in the model. So while the actual vegetation fraction of 0.6 was the same, there's no ability for the NOAA MP slab model to have vegetation at all, so it just was all coming out as zeros.
Cool. Well, thanks everyone. appreciate you coming today.
Thank you.